Hello everyone, I'm Shravan. I will be an assistant professor at UT Austin starting next year. And today I'm going to tell you how you can secure your applications from bugs in its dependencies. So this work is actually a multi-year collaboration between a bunch of folks at UC San Diego, UT Austin, and Mozilla. And in a nutshell, today's talk is about this technique called in-process sandboxing, which is a way to secure your native code dependencies. And this idea of in-process sandboxing is actually an old one. It's been around academia forever, like 30 years. And we've finally been able to bring it into production. And to do this, we had to build this framework called RLBox, and which is a framework to make in-process sandboxing practical. And what RLBox lets us do is sandbox any libraries or dependencies we don't trust and continue to use these dependencies in our application. And the sandboxing is done with WebAssembly. So Firefox has actually adopted RLBox and is shipping with RLBox for over 2 years now. And this is something we believe other applications can start doing as well. And so in this talk, I'm going to give you start with like the high-level bits of the motivation, why we want something like in-process sandboxing in the first place. Then we'll talk about some of the pain points of in-process sandboxing and why we want something like a sandboxing framework to help us adopt sandboxing. Then we'll talk about RLBox, and I'll end with some of our experiences deploying sandboxing with RLBox. And so let's jump right in. So the reason we care about any of this stuff I'm going to talk about is almost every application we use has native code in it. So that's C and C++ code. And as you probably well know, native code tends to have memory safety bugs. And if you've been to a talk about memory safety before, you've probably seen these graphs. So these are analysis conducted by Microsoft and Google on Windows and Chrome, cataloging all the bugs they've seen in a period of 5 to 10 years. And what they found was that 70% of the bugs they see are the classic memory safety buffer overflow, use after free, and that sort of thing. And at this point, if in case you're already checking out saying, well, who cares? I'll just write stuff in Rust and it doesn't matter, right? Unfortunately, safe languages like Rust, Python, all of these things are built on these same unsafe libraries written in C and C++. And just as a simple example, right? A lot of these applications we write depend on, let's say, OpenSSL, 500,000 lines of C code right there. And if you want a fun thing to do, just open up the Rust package manager and look at everything that depends on CC, which is native code, the native code crate. And the problem we have with this situation is that native code bugs, native code library bugs, are a real problem because they're used in real in-the-wild attacks. So we've seen this sort of thing being used to compromise applications like browsers, like smartphones, iMessage. The list is almost endless, actually. And none of the defenses we have at our immediate disposal really work. So we have things that harden applications, ASLR, stack canaries, control flow integrity. Hopefully some of these things are familiar. And the overall takeaway is these things help, but they're kind of speed bumps for attackers. They bypass these things quite routinely with some effort. And the other approach is, well, let's say we're going to rewrite everything, like everything in Rust. Unfortunately, we have over billions and billions of lines of C and C++ that are not going to get rewritten overnight. Because rewriting something in Rust is not just the syntax change. You need to retest it, get it up to feature parity, performance parity, cross-platform support. There is a whole bunch of work that goes with rewriting a library in a new language. And this is not even something that Firefox, who developed Rust, is attempting to do with their browser. And so let's consider a different approach, right? So there is another way, which is we can take all of this code we don't trust and just stick it into a separate process where it can't hurt us. And this idea of process sandboxing has also been around for a while. And on the one hand, it's great because all of the code we've been already relying on is the code we're using, so we get code reuse, which is awesome. On the other hand, even though this idea has been around forever, apart from a couple of exceptions, which is web browsers and OpenSSH, I don't know of any applications that use it. And this is kind of for a very good reason. When you use process sandboxing, there are multiple processes. And when you have processes, you have IPC, or inter-process communication, and IPC is slow. It has a performance overhead that will be visible in your app. And almost inevitably, if you kind of go this route of splitting your application into processes, you're going to have to re-engineer your application. You're going to have to put substantial effort in dealing with some of these overheads. And so it's not easy to retrofit this sort of process sandboxing into your application. Now, I could talk about all of this at great length, but instead, let me just point you to a talk by Chris Palmer, who goes into all of this in great detail. So instead, today I'm going to talk to you about a different technique called in-process sandboxing, which is a technique we've used and found does work to address this problem. And in a single line, what we are doing is we want to isolate the libraries that we are pulling in WebAssembly sandboxes, right? And for the purpose of this talk, it's enough to think of WebAssembly as a compiler that compiles code like normal, but inserts runtime checks before memory accesses. And the goal of WebAssembly, or the goal of doing this sort of thing, is to convert your application from this one monolith with all of the code components jammed together with a single address space to one that looks more like this, where components are separate, components, code, and data are separated from each other. So in this example, libjpeg is separated from the other components, and libjpeg is restricted to OX 4100, OX 4200. And the idea here is, even if you have a buffer overflow within libjpeg, it can never affect the memory of the rest, other parts of Firefox or other code components. So this is what this sort of sandboxing will give us. And the advantage of this in-process sandboxing is we've got rid of the processes. We've solved our performance problem, which I mentioned earlier. There is no processes, there is no IPC. The CPU and memory overheads are actually very modest. So this is great. Unfortunately, we're still left with a slightly difficult problem of engineering effort. We still haven't figured out how we can take something like in-process sandboxing and put it into our application, right? So let's dig into that a bit more. I'm going to talk to you a little bit about what it's like to adopt sandboxing and basically try to lead us to the conclusion that we need a sandboxing framework, because it's rather difficult to do this by hand. And perhaps the best way to visualize all of this is with an example. So we're going to go through an example, which is we are going to go through the process of sandboxing libjpeg from the Firefox browser, right? So step one, super simple. We're going to grab the libjpeg sources, unmodified exactly as is, and run it through a WebAssembly compiler. And what WebAssembly is going to do is produce a sandboxed libjpeg binary, which we are now going to use. And what WebAssembly is doing under the covers, again, is just adding bounce checks to memory accesses. So concretely, you can think of it like this. If you had a pointer dereference, what WebAssembly is going to compile that as is a bounce check followed by the same pointer dereference, right? Now, I should point out that real WebAssembly compilers do use quite a lot of tricks to optimize away that bounce check because you don't want that performance overhead, but that is the right intuition. That's all WebAssembly is doing for us, right? And the even higher level takeaway from all of that is we broadly know how to do this. This is the solved bit to some extent. The part we are still kind of grappling with is how do we now modify Firefox to use that sandboxed binary? And I'm going to, for the rest of the talk, that's the part I'm going to focus on because that is, in a sense, the difficult bit at this point. And concretely, when I say modify Firefox, we end up having to do a few different things. The first thing we really want to do is decouple the library from the application. So Firefox and libjpeg at this point, because all of the features are already written, share a lot of code, share a lot of data and control flow, and all of this is deeply, deeply intertwined. So we have to now spend the effort to separate these things. And once we do that, we now have to re-enable this data sharing in a more controlled way, in a way that we can track what's happening and allow only the data sharing that we actually want. And this turns out to be tricky for a couple of different reasons. So one is a low-level reason, which is the WebAssembly compiler has a different application binary interface, ABI, than the rest of Firefox, than the host application. And this is for some performance reasons that I won't get into, but that is the reality. And what this means for us is any shared data structure, the sizes are not what you might expect, or the calling convention is not what you might expect. So we now have to go in and add a bunch of code to fix up these things, fix up these ABI differences in the form of data structures, calling conventions, and all of these things. The other bit we have to do is actually marshal data between the different components because each of them are living in different portions of memory. And we can't be too sloppy with this sort of marshaling. We need to do it very carefully. We need to do it in a lazy way. Else we're going to introduce a lot of performance overhead just because of the data marshaling. So there's a couple of challenges in doing data sharing right here. And once we finish all of that, we now have to think about security as well, which is the starting point of all this. Which is, if you remember, Firefox is written to use libjpeg, assuming libjpeg is trusted. But if we now say, well, we don't trust libjpeg, we want to throw it in a sandbox, it also means we can't trust any of its output. So we have to go to all of the places Firefox uses libjpeg output and sanitize that data before we use it. And the easiest way to visualize this is code. So I'm going to show you some code. Don't panic. It's relatively small. So this is a 10-line example of an application that uses libjpeg. Don't worry about reading all of that yet. The takeaway is it's an application. It has some JPEG APIs. It wants to parse an image. Now, if I make all the changes to this code that I showed on the previous slide, which is, marshal data, and disentangle things, add security checks, the resulting code is going to look like this, which is every line of code has changed. And if you attempt to read that, which I really, really, really don't recommend, it is almost impossible to parse what's happening. And it's worse than being not readable. If you make a single mistake on any one of those lines, your app is likely insecure. You've completely defeated the purpose of your sandboxing. So hard to read and security critical. Yay. So needless to say, our conclusion is this sort of manual approach of like going in line by line, changing all of this, is going to fail horribly in practice. Real systems are much, much larger than this 10-line example I've showed you. In fact, the same component in the actual Firefox browser is, I want to say 3,000 or 4,000 lines of code. So you can imagine how big that diff is going to be if you do this by hand. And the other problem, which is more fundamental when you look at that sort of diff, is we've exposed all of the low-level details of sandboxing. And the resulting code is really unmaintainable. And for example, if you think of any line of code in that diff, who maintains it? Is it the security team, the feature team? It's really hard to tell, right? And imagine you now have to change that code a little, maybe add support for a different set of platforms, add some debugging or testing features. It's going to be really difficult. And even if you can somehow do all this by hand because you're an expert programmer, now multiply this effort by every one of the libraries you want to sandbox. And so we tried this. It really didn't work. And we weren't even alone in this sort of trial and this sort of conclusion, right? So folks at Google also tried to do this and came to pretty much the same conclusion as us, which is you can't do this by hand. So it's to solve this problem, we built the RLBox framework. So RLBox is a type-assisted framework, type-directed framework that will help adopt sandboxing onto your existing application. And RLBox uses types to assist with a whole bunch of things, right? It uses types to hide the low-level sandboxing details. So things like marshalling or ABI conversions, all of that is completely automatic and automated. You won't see any of it. Next, the types also track untrusted data and untrusted control flow. So if you now forget to add a security check in all of the places in Firefox code where you're supposed to, RLBox is going to give you a compile time error. And finally, types also let us make all the changes to the Firefox code incrementally. So we can make some of the changes, pause this migration process, we call it, and compile and deploy even. And perhaps the best bit about all this is RLBox is just a pure C++ library. So there's no compile time tooling, there's no, all of your compilers stay the same, build systems stay the same, and so on. And at a high level, RLBox is pretty simple. It's just 3 principles. The first one is all control flow has to be explicit and go through RLBox. So if you're calling a libjpeg API in your application, JPEG read header in this example, you can't call it directly. You have to go through sandbox.invoke. Right? That's the RLBox API. Now, don't worry, if you forget to do this, you will get a compile time error. The second principle is any data coming from the sandbox code has to be marked tainted at the type level. So if you access the size of the JPEG image from this shared data structure that holds all your metadata, it's not a U32, it is a tainted U32. And again, if you forget to make this change in your code, you will get a compile time error. And finally, if you use tainted data in operations, without checking it, you will again get a compile time error. So here, if we use this tainted size in a mem copy, that's a compile error. Instead, what you have to do is verify the value of size with this API called copy and verify, and that's what will actually pass. Now, alternatively, if you don't want to start wondering about what the right value of size should be and so on, you can temporarily throw away the tainting. There's this API called unsafe unverified, and this allows you to kind of pause the migration process, as it were. And that's pretty much it. That's all of RLBox in a slide. So I'm going to go back to that same example, and this time use the 3 principles and RLBox to do the same code changes. And to start, the first step here is to create what we call the so-called no-op sandbox. Now, as the name implies, this doesn't really sandbox anything. This is just to aid with the migration process. And after that, I'm going to focus on changing just the first 4 lines of code, right? So I'm going to ignore the rest of the program for a second. And in these first 4 lines, I'm going to apply the first 2 principles, which is variables are tainted, function calls go through sandbox.invoke. And if I do that, I will basically get the following code. It is only a syntactic change, but I'll pause to give you a second to look. The one thing you might notice is I've also renamed the variables. That's just for convenience reasons. You'll see why in a second, but it's purely a syntactic change so far. Now, if I go ahead and compile this code, this will actually tell me something, because RLBox is set up to give you compile time errors, and these errors are meant to be helpful, even though they are C++ errors, which are, tend to get quite long. But we have set it up so that the error messages are helpful and guide you. And if you don't get an error in these first 4 lines, this is RLBox's way of telling you, well, all of the code changes you've made so far are correct. So if I actually do compile, I do see an error, but it's later on in the program, which actually tells me, yay, the first 4 lines are done. I don't have to do anything more there. Now, we've done a bit of work so far, and we might have a question, does all of the stuff we've done so far look okay? So I want to pause the tainting process here and check if my application still works. And I can do this with a single line of code, which is calling an unsafe unverified on the tainted data. And again, I'm going to pause to just give you a second to stare at that one line. And if you look at it, there's nothing particularly clever about it. It's just a variable naming trick, right? We've removed the tainting, and we've just assigned it to a variable called JPEG image, and then the rest of our code looks like it should compile. And in fact, if we try this, it does compile. In fact, it does better than compile. It will run, it'll pass every test. You can even deploy it to production in this state. And we actually have deployed applications to production in this state. And this pattern, we call this the unsafe alias pattern. And this is what really helps us migrate the code incrementally. And just to kind of drive this home, say I want to migrate just one more line in this function, right? The line that's highlighted below the yellow one. Then the way I would go about it is to move my unsafe alias one line below, make the change to the line that I've just jumped over, and attempt to compile it. And in this way, we go through this loop of changing each function, changing it line by line. And if we finish this process, the code we're going to end up with looks something like this. And right away, without even reading it, I hope you can see that it looks a lot more readable than what we had earlier. And let me point out 3 particular things with this code. The first thing is RLBox is going to handle all of the ABI differences. And that, in large part, is the reason why this code remains readable. There's no low-level muckiness about it. Second, RLBox is even going to add security checks where it deems necessary. So it's a little hard to tell in this example, but the line being pointed to is actually your application dereferencing a pointer given to it by libjpeg and writing to it. You definitely need a security check or a bounce check before doing that. And RLBox knows that and is going to add that check for you, so it's not even going to bother you with it. And the third thing which is interesting about this code is the size variable is tainted. And this hopefully makes sense. Size is a variable that's computed based on the width of an image and some other metadata, all of which comes from the JPEG image data structure, which itself is tainted. Therefore, size is tainted. And if we go ahead and compile this code, we're going to get an error saying, oh, you have a mem copy which uses a tainted size. And to proceed, we need to remove this tainting of size. And as we saw earlier, we can do this with an API called copy and verify. And if I go ahead and make the change, it looks something like this, where I'm verifying the value of size, and I have to pass in a safety condition. And here the safety condition is that the value of size should be smaller than the output buffer, which is sufficient for this example. Now, I should be very clear here. What RLBox brings to the table is this observation that, oh, you are missing a security check there. Now, it doesn't tell you what the security check is. It doesn't even tell you if you got the security check right. It's just telling you that you probably need a security check there, and I will give you a compile error until you put something there. So it's still on you as a developer to figure out what goes in that verification condition. But at this point, if we try to compile this, everything actually goes through, and we're nearly there. There's just one last step, which is actually in the first line of code. So if you remember, we started with this thing called the no-op sandbox. So we want to change that to something that actually enforces sandboxing, something like WebAssembly. So we're going to make that change, it's literally one keyword, compile again, everything works, and we're actually done. And this is what RLBox brings to the table. It gives us a systematic process to make the changes to our code, and also gives us closure, right? We know that we are done, as opposed to what I showed you earlier, which is it's not clear where the beginning and end is. And if we take all of this together, what we get is with WebAssembly and RLBox, we get the 2 things we were looking for, which is fast sandboxing and low engineering effort. And just to see how all of this kind of shapes out in practice, I'm going to tell you a little bit about our experiences using RLBox and deploying it in production. So first things first, to actually check whether RLBox is making adopting sandboxing easier, we started by just taking a bunch of applications and sandboxing a bunch of libraries. And these libraries were different types of libraries, so things like image rendering, font rendering, audio playback, XML parsing, spell checking, a few different types of libraries at least. And what we saw across all of these things is that RLBox really helps, the automation of RLBox really helps. So RLBox is able to automate away dozens to hundreds of security checks, dozens to hundreds of ABI conversions, and so on, and it left us with very little manual work. Usually, it's just in the form of tainted data verification, which takes about 2 to 4 lines of code in each instance. And all of this meant that we could sandbox a library in an application in a matter of a few days. So after this, we turned to production, and we wanted to get RLBox production ready. And we worked closely with Mozilla to do this. And in February 2020, we actually shipped RLBox as a part of Firefox. And since this is research code hitting production, we wanted to be very careful, started very small, a single library across just the Mac and Linux platforms. We sandboxed, in fact, the font rendering, right? And since that time, we've been working to improve RLBox's portability, its performance, debugging, a whole bunch of features across the board. And at this point, we've sandboxed a handful of different libraries across multiple features across all the platforms Firefox supports. And this includes, on my Android smartphone as well. And on the performance front, I also wanted to tell you a little bit about the overheads we saw, because sandboxing is not free. It might be low cost, but it's not free. And I picked out a couple of the more performance-sensitive applications we sandbox, or features we sandbox, which is XML parsing and font decompression. And in both cases, we saw feature overheads of about 10%. Now, this is not nothing, but it's hopefully like below some threshold, right? Like, what this really lets us do is, as developers, we get to make the cost-benefit analysis of whether this is okay for us. Now, in the context of browsers, if you had a 10% hit to one feature of the many thousands of things a browser is doing before it renders a web page, that slowdown is not going to be perceivable by an end user. So we are okay with this. But definitely, this sort of reasoning has to be domain-specific. In the browser, this works out great. I'm also happy to talk about the overheads we saw in other applications offline, so come talk to me if you're interested. But broadly, this let us ship RLBox in Firefox. And we aren't done. We are still working on a whole bunch of things, starting with like performance features. So for example, WebAssembly is still in the process of standardizing what things like threading looks like in WebAssembly. So we are following all of that because the moment they add support, we also want to make sure we're supporting it so that when we sandbox libraries with threads, we get a reasonable performance. And something we're doing from our side is to optimize implementations of WebAssembly, especially for low resource environments. So one of the things we care about is reducing the virtual memory footprint on 32-bit architectures. The implementations we have are pretty good for memory overheads, but virtual memory is also something that is of a premium in 32-bit platforms. And so we've been working on that to reduce that overheads as well. And finally, on the usability front, we've also embarked on this effort to revamp the RLBox APIs to make it even easier to use and have a tighter integration with modern C++ idioms and so on. And so, help us get this right. Try it out. Try out RLBox in your application. Tell us what works. Tell us what didn't. We're happy to have a look and even help out if possible. And if you're interested in something like bug bounties, RLBox is a part of Firefox and is therefore covered by Firefox's bug bounty. And it's actually even better than that. RLBox is covered under a sandboxing bug bounty by Mozilla, which means you can take any library that is sandboxed with RLBox in Firefox, add a memory corruption to it, buffer overflow, use after free, whatever you want. And if you can use that to break out of the sandbox, you get your bug bounty. So this is great. This works out great for everyone. We want to secure things, and if you want to play with attacks, there you go. So in summary, in-process sandboxing is this technique we are using to secure our native code dependencies. RLBox is a framework that helps adopt in-process sandboxing into your application and lets you sandbox these native code library dependencies with WebAssembly. And RLBox has been shipping in Firefox for over 2 years now. And we believe this is something that more applications can use to secure their dependencies as well. So thank you, and I'm happy to take questions in the time I have left. So the question was, what was the reason to start with font rendering? It was as a sandboxing target for Firefox libraries. It was actually a mix of a set of different factors. It so happened that the particular font rendering library had recently undergone a security audit. And there was some concerns based on what was found in that audit. So it seemed nothing too like, oh, it has this CV and we have to, but just some general concerns. And so we chose to sandbox that. It actually turned out it was a particularly tricky one to sandbox just because of the interface was particularly complicated. So it actually wasn't based on ease of sandboxing at all. And one of the assessments we had was the performance, as you raised, the performance concerns, right? Which is, we want to start by sandboxing something that is not too far into the critical path with respect to performance. And this hit that criterion, which is, it is important for performance, but it's not the single bottleneck. And because usually network latencies tend to be the bottleneck in the browser. So it was a combination of those things.
Can you talk a bit about how fix the memory segments for isolation for sandboxing?
Okay, so the question was how RLBox picks the memory segment for isolation. So There's a couple of different ways I can interpret that. If you're talking about literally which address to put what, that's, it's dynamic. I showed it with simple static numbers. It's completely dynamic. But beyond that, oh, the mic's cutting out, sorry. Yeah, but beyond that, it is completely based on the library and its data, right? Like, so if you're sandboxing a particular library, it gets its own private heap is the way to think about it. And so for every library we choose to sandbox, libjpeg, libogg, or whatever, they all get their own heap. And that's just a region of memory that is isolated from everything else. And Firefox, of course, operates on the global space, whereas libjpeg has its own thing, libogg has its own thing, and so on. Did that sort of answer the question? Yeah, that's a question. So, which is what is the size of these different memory segments? So it is growable. WebAssembly has some limits, which is the current WebAssembly standard says you can't grow more than 4 gigs per instance. There is a newest, different WebAssembly standard called WebAssembly 64 that allows you to have larger heaps. But for the examples that we've picked, this 4 gig limit is sufficient. And it does grow. It starts with a simple 4K page and grows. So the question was, did the other memory sizes fix at compile time, or do they grow? No, it's again completely dynamic. It's just like how your heap in your regular application would grow based on demand, which is you would call something that looks a lot like sbreak, and that would expand the size of the heap that's available to you. Right. Going once, twice, and sold. Thank you very much.